From what Professor Eager's been talking about in terms of material selection and economics for materials. We're going back to this series on overview of materials processing. If you remember, I started talking about casting in general, and then we went into more details on solidification. So I was mentioning that the bulk of the materials we use are wrought products, so they go through casting, and then there's a lot of deformation processing. But there are a lot of pipes and fittings and valves, like the one I'm showing here, that are used as cast. They come out of the mold, and then you machine just the surfaces where you have to make mechanical connections. We've talked about some of the detail process. You have a wax pattern on the upper right-hand side, where essentially you can make any shape you want here and put it in a slurry to make your casting mold. And when you're done with that, you melt the wax, and you have a hollow cavity to cast the different parts that you're looking for. So now there are a lot of systems there in terms of risers and making sure essentially that you have a little extra room for the liquid, so any contaminated liquid is not part of the critical component that you're trying to make. It's just get accumulated in another piece. Like this whole tree going up, these are jewelry items, and the whole tree going up and even on top is not something that we're interested in terms of parts. So it's going to be scrap metal that's going to be reused either for casting after it gets purified again. We talked about die casting for aluminum wheels. That's the lower left. And I think I emphasized enough that one advantage there is you get a bigger cooling rate because you get the metallic molds as opposed to ceramic or refractory molds or sand molds. The other aspect, it's under pressure. So what we were talking about, the little experiment with the heat transfer with the mold, if you keep applying a pressure, you help maintain a good heat transfer coefficient. And you also make more sure that it's going to be homogeneous through the wall. We, at the very end, discussed that instead of having this dendritic structure and having a casting that has a lot of orientation, you can cast essentially a semi-solid fluid that already had solid in them, a little bit like doing when you have concrete. You get the aggregate, and then you got the cement. So you're sort of predetermining the microstructure by having already solids in there, and these will grow a little bit, and the space in between is where you have your local solidification. So you avoid having the big dendrites starting from very close to the mold surface and going all the way to the inside, which is not atypical in certain alloys. So again, we talked about these heat transfer experiments and how the mold affects the nucleation and growth of the solid on the surface. So today we'll talk about plastic deformation. If you remember at the very end of last class together, that was middle of last week, I said in elasticity you stretch the atom, so you're really working with the energy function, the equilibrium position between the atoms, so you get them out of the equilibrium. And that's why when I pull, I spread them further apart in the pulling direction, and then they try to get closer in the other direction to minimize the overall change in distance. And that's the Poisson's effect. When we talk about plasticity, there's something that is very important. Plasticity doesn't change the volume of material. All you really do is you move things with respect to the other, but your average atomic distance when you're in pure plasticity mode is the same. And therefore, you go through all these processes, you make dislocations. We'll talk about dislocation. You'll see it's not scary. And the volume remains the same. It becomes useful when you're trying to do the analysis of a process. If you have a certain process and you know what's going on, you know the pulling force, and you're going to know how much you're going to reduce the diameter with that respect. So conservation of volume in metal plasticity unless you're about to break. And that's not something I'm going to discuss very much here, but it's something that I discuss in details in the spring lectures. Okay, probably most of you are familiar with the tensile test. I have here some duck bones that I'll circulate around very quickly when we understand a little bit what I want you to see here. So you start with one of those specimens. As you pull on it, you can see this one. I matched approximately the fracture surface, and it's significantly longer, at least in this gauge section. So if I had originally this length of constant, then here I'm about 50% longer. So that's what we call a 50% or 60% elongation at break. On that curve, what happens is this is something a lot of even mechanical, structural, all engineers struggle with, including some of the best ones, where you look at the stress-strain curve, what you see is you have the elastic behavior at the beginning, way over here, up to what we call the yield point. So up to here, the Hooke's law apply, and you have a Poisson's ratio, and if you let go the load, you'll come back to the same point. When you start seeing the deviation from linearity for metal, it means if you come back with a slope that's parallel to this one, and you'll have a permanent deformation. Now, anywhere between the onset of plasticity and where you have the load M, you keep stretching your sample, but the whole section, the gauge length in the middle, remains constant. So a good example, this is very close to what happened. So it's stretching here, and I ended up with something a little longer, but it was the same deformation through the whole gauge length here. When I reached the peak load, the maximum there, what happens is all of a sudden I have necking. So the deformations start to localize in one area, and the apparent resistance of the material starts going down. You can see what we're showing here is the stress, but it's actually the way the stress is calculated in all these outputs. If you go to the lab, they'll essentially take the load applied, the load sensor on the machine, divide by what was the original area of the material. It doesn't take into account that your cross-section here, the value of A, the area, is reducing. And therefore, you of course get a value of P, and then all of a sudden you have one area, the area is really shrinking, but it's not taken into account in the calculation of the stress, and therefore it looks like the material is weakening, right? It's going down. And then eventually you have a final fracture, and what we call the elongation at break is after the elastic return there. Okay, so going to the the necking process, you can see it on essentially a bar that was originally a certain diameter. It was deforming already, so this has been deformed. But you see the curvature, you see very close to the fracture surface, these are matching with each other. Very close to the fracture surface, you have this local effect where you reduce the area. And again, it's not something that's taken into account in the stress-strain curve. So what happens in that reduced area? You have more strain, right? If we say that the necking is going to happen right in the middle of the specimen, after you passed the stage C here, when you're at D, you have all the extra plastic deformation taking place in that neck, and it keeps going and going, so that your strain level is much higher. Typically, you have a strain that's about twice. The total strain is going to be about twice what it is in the neck than it is in the remaining section of the material. So if you did, I'm going to skip one slide here. if you did account for this reduction in diameter in the neck zone, what you would find is there is no such thing as the weakening of the metal. The metal continues to harden. You can see when you transfer the peak stress, what we call the engineering stress, when it's determined by load divided by nominal area. When you make the correction to make it the actual area, you see that there is an upward slope there, and it really just keeps going. Now, there are simple equations to make all that transformation. Some of that actually, and Hertzberg I'm listing there is what I find the most simple demonstration. He actually goes through the conservation of volume to derive all these relationships. It's not that straightforward. I don't even think there may be an integral, but it's a very easy one. One of the known fact is conservation of volume, and that makes it makes it unnecessary to go through some of the details and actually put in gauges to figure out what's going on. Now you can only make the correction up to the peak load here if you use the stress strain curve. If you try to extrapolate beyond that, you would need to know the diameter or the area in the neck zone. But what we normally do, this comes very important if you working on a team where someone is using finite element analysis to study how something is deforming. You have to put in material properties, and a lot of times all you have is the stress strain curve. So if I only have the stress strain curve, I know that for my computer program, I need to tell them that there's actually hardening, because the computer program knows everything about the reduction in cross-section. It can essentially work with the actual stress-strain behavior of the material as opposed to the engineering representation that we use. So what we do typically is we use a power law regression, and we extrapolate. So where you get the C prime is not really by working with the C, it's just extrapolating the best fit curve that we can get between the beginning of plasticity up to the B value, the peak there. So why are we doing the regression? There's a lot of experimental studies that show this power law relationship where your stress level is function, the flow stress. This is plasticity. This is, we're deforming the material with past Hooke's law, and essentially it's saying as I keep deforming, I'm going to increase my flow stress. It makes sense because you've heard, I'm sure, about grains and dislocation. When you really just start to work them, everything becomes more and more tangled. And that's what brings you extra resistance to the deformation. So that power law applies to most metal, and it's very useful because it prevents us from having to do very sophisticated experiment where we'll either study what's going on in the neck or load the material in bending or in compression in a way that we don't get the neck. The necking in the tensile specimen just really comes as an instability. It's the point, it's a geometrical effect. If I do everything in compression, I would essentially get, right away I'll get the curve that goes to the C prime going up because I don't have the formation of that neck. There's no kind of a buckling phenomena. It's a tensile instability. It's not buckling, but it's all of a sudden what happens if I have one element in the material. Let me try to find something good here. So I have a duck bone, and I'm starting to deform, say, right here. So I stretch this big element, and it turns out, say, it's looking like this now. When I'm at the beginning of that curve here, my strength in that cube goes up a lot. So what happens in practice if I have just a little instability at the beginning? So we're going to say in the A to B zone. And then we're going to be in the B to C zone. What happens here is the strength goes so high. So if I have this at the beginning, this plasticity is going to stop, because even though I've lost a little bit of width, I gain so much in my strength that that's enough. So then I'm going to deform a little bit here, and deform a little bit there, and it just keeps going as a regular process. If, on the other hand, I have a situation where the hardening is still there, but just not sufficient, right? That's what happens when we reach that point B to C. You have this cube, okay, so I ended up with a little less cross-sectional area. And then the next thing I know is that same cube 1 is continuing to deform because it's the weak point in the chain. If you've heard of bulk metallic glasses, for example, on metals, they behave this way almost right from the beginning, because it's completely disorganized and there's no real way for the material to gain strength by deformation, that it will start to neck and localize in the middle or in one area right from the beginning. It doesn't mean it breaks right away, but it's what you're measuring is the straining of one area. And maybe on a bulk metallic glass, those I've studied say you get 6 to 8 elongation at break. So say the strain to fracture. In reality, in that zone where actually the form of strain is much higher. So it's just because we were making our reference with respect to the whole cross section when we calculate that strain level. Keep it in mind, please, because I've had to correct too many people on this, practicing engineers with engineering licenses and a lot of credentials, a lot that you would think you could trust them. All right. Now, let's move to something a little more interesting. I'm going to distribute these guys. So on the right side, you have 3 pieces of copper. It was the same alloy to begin with. And what happens is they were heated and at these temperatures, so 450, 600, and 700, for the same period of time. So you start from one material, you heat it to recrystallize it, to soften it. And you can see that. You can see that at 700, the material deformed quite a bit more than 450. One thing that hopefully the light allows you to do, I may have to bring up a little more light. The middle sample, the one at 600, you can see what we call an orange peel effect. So you'll see an effect of the grains here that you don't see at all at the lower temperature treatment. And you see it a little bit at the higher temperature, but it's not quite as big. So when you think about it, it's not linear, right? So no grains visible, a lot of grains, and at the higher temperature back to kind of some effect of grain, but not as big. So there is a peak there. The side is same testing condition, but it's a 2-phase alloy. It's a brass alloy. And what you'll see is even at 600 degrees, there is hardly any effect of the grains and how it plastically deforms. So I'll pass it around. You can move it, you can play with it. Let's see what I can do here. No. Does it help or make it worse?
That's good.
Yeah? Yes?
So with the metallic samples, when you're going from like A to B, you're aligning your dislocations, right? It's like what?
You multiply them.
And multiply them.
Yes.
So I guess physically what's happening then when you go from B to C, are you then actually create, like what physical phenomena?
It's the same physical phenomena. You still have dislocation and multiplication, but you just don't have enough to resist these little instabilities. So if I take a piece of copper for, say, electrical lines, it's very high purity, and the only way they want to use it and hang it from one transmission tower to the other is in very, very stretched condition. It's work hardened. Now, it's so work hardened that when I pull on it, it doesn't really want to harden anymore. It's beat up to death. And therefore, it will be necking very early on. So it will show like it has no ductility whatsoever. But what happens is it's pretty much at C prime up there already when you put it in service. Now, this flows nicely. Dislocations. It's not about them moving. If they were just moving, really, we wouldn't be able to use metals the way we do. Because one atomic distance going across the sample, you don't see it. You know, if all you have is one dislocation that goes from one side to the other, I cannot see it. You need millions and billions and trillions of them to start seeing something. Now, how do we get trillions? There are a lot of mechanisms to essentially produce dislocations from nothing, well, from stresses. And the way you do it is, say I have, and bear with me for a second on what a dislocation is. A dislocation is a line defect. And say that in a certain grain, I have it organized here, and it's held in place at 2 points. And you can probably think of many ways why it will be holding at a point there. There may be a precipitate. There's probably something that's taking it from moving at that location. So what happens under stress, the part of the line defect, the dislocation that's able to move, is just going further and further away, and I keep increasing, and there is some energy spent in doing this. You know, I'm not going to deny it. But there's no net volume change. You create as much tension and compression. So I go from just a very small segment, and I grow it, I come back. Now it's touching, and I'm able to separate a complete loop, a complete dislocation loop, and I still have my segment to make a new one. That's dislocation multiplication. I only had one bit to begin with, and then I can make thousands like this. And they'll keep going. They go away and they start interacting with the others. They make more of these anchorage points. And then all of a sudden you start having them on other planes, and it just goes crazy. Okay. Now, what exactly the dislocation is? Yes, go ahead.
What do those points and lines signify actually?
These.
No, the previous line.
Yeah, but it signifies the points here are a location where the dislocation is either changing completely orientation. So say it was on a certain slip plane and it's going to another slip plane, so it can't really move at that location because they have to move on 2 planes at the same time. Or it could be, you will see that when we talk about strengthening mechanism, it could be interacting with something else in the microstructure that prevents it to move at that very specific point, a little precipitate. The line is the dislocation itself. It's a line defect. Does that answer yours as well? Okay. All right. Now, I took a little bit of time to select this one image. This is as deep as we're going to go in terms of dislocations. This is about 1/8 of a full 3D cube where we essentially create a dislocation loop out of nothing. You see the dislocation burger vector here. So this indicates you the direction of the movement of the the atoms. Essentially, if I take everything on that plane, on that circle, and I just move it a little bit, that's what I'm getting. I'm getting 2 types of, well, I'm getting a full loop of dislocation. I had nothing to begin with. And then all of a sudden, I have zones of tension and compression. Like over here, I have an extra atom, and I have one atom less down below. If I'm looking here, it's twisted. So that's the screw dislocation. But it's really came out of nothing. Now, that's not how we create them. There'll be a lot of energy making that displacement all at once. The way they actually create it is that Frank Reed's source I showed where it's spin and it just moves gradually, and it's so low energy. The only real obstacle to the dislocations helping deform in the material is when they start hitting each other. When they come from different direction and they hit each other, that's where you form elements of resistance. There's very little resistance associated with just going on and making the dislocations in metals. If you're looking at ceramics, completely different story. Here we're looking at a single crystal. I just really want to make sure we're all convinced that this is happening. It's a single crystal. The only thing that happened to it was deformation, tension, compression with plasticity. Every little interface that you see there are not anything related to other faces, inclusions, different grains. This is a single crystal, and yet it has all these zones. This is transmission electron microscope images, so we're looking at a very, very small scale into that single grain crystal. But hopefully you can appreciate, you see this very sophisticated dislocation structure. So you have that ladder, for example, that got a lot of people excited the first time they saw it under the microscope. What it is a zone in the crystal that has very little density of dislocation, and all the dislocation are stacked up in those planes. So if when I come again to make a deformation, all I do is I'm taking some dislocation somewhere and I'm having them travel to the other side. I form that stable structure. Not necessarily this one. This one will come and disappear, but there are dislocation structures that essentially, if I keep deforming, I should show you that because that's important. I'm doing this experiment by controlling the strain. And I'm going to show you, no, it's a fixed strain, so I'm looking at the stress level. So we have fixed plastic strain. And we're looking at the stress level over time. If I had a material that was low dislocation density to begin with, so I'm cycling it, and all of a sudden, oh, my load's increasing, and then eventually it's going to become stable, so it dies off. So the overall curve that we can see, say the stress over number of cycles, I'm going to put n here. And I could put time, it doesn't matter to me. I can see my material is going towards a plateau. It's very, hopefully something that you can tie to what we're saying there. Because when you reach these structures where the dislocation, oh, you have more energy, okay, I'll give you one more. I just have enough because I created these zones that are filled with defects. And what it takes to go from one side to the other is just to bend enough based on the size of this area. So the stress, you still need the load, but from one time to the other, the structure stays the same. So if you come with the same load, you get the same strain, and it becomes stable. Now, I'm mentioning it in terms of cyclic deformation. Just go ahead.
I don't know. Would you mind just explaining what gives rise to like black and white regions? Like
Black is high density of screw and edge dislocations, and you have both of them. Now, there will be some very detailed study. They'll tell you that those are mostly edge, some are mostly screw. I can't remember that. I don't know which one is which. But think of it as one grain that has all this internal defects that act as your mechanism for being able to deform back and forth. You're imposing a plastic strain here. Yes, yeah, it's a cross. When you look at the TM, they have to be very, very thin. It's by transmission, so it's kind of looking through the entire thickness of the sample, but it's so thin, the sample, that you're looking through a single cell of dislocation. You would have a similar effect if I just pull on the material at ambient temperature. When I do cold rolling at ambient temperature, I beat it up. Okay, I'm getting the steel, say, 3-4 times stronger than it was when I started out of the mill, but I'll eventually also reach a stable dislocation structure. It's not going to continue to harden forever. There'll be a point, and for forming of steel sheets, it's not exactly cold, sometimes it's warm. It's around 300%. When you reach 300% of real strain, even if it's just pulling one way, you have a similar effect where you have the cell walls, and your structure inside each grain becomes about the same over time. And that's actually how I can best introduce to you the concept of recovery. So if I have restoration, what we call it, both are similar. Restoration is more of a reorganization of the dislocations, and recovery is when you have, say, you take a positive dislocation plus a negative one that gives you nothing. You essentially are healing the material. To get to this, you have that going on all the time. Yes, please.
So when you have dislocations clustering like that, why are then grain boundaries not formed? Why don't they?
There's no grain boundary. It's a single crystal here.
I guess that's kind of my question.
Yeah.
Why don't dislocations result in a single crystal turning into a polycrystalline material?
Okay, perfect. This is your crystal. If it's copper or aluminum, it looks like this, but you only have the black items. Just forget about the brown here. What happens is you have 12 ways, 12 planes in which the dislocation like to be and move. These are the slip systems, right? So you have one dislocation, another dislocation. They are in so many slip systems. There's only so far that the dislocation will physically be able to move in the grain before it gets too tangled with the other ones. And that essentially defines the spacing here, kind of the free moving distance for one dislocation. So say I'm moving back and forth, tension, compression. I have the dislocation here. The next reversal, it can go back to where it was and just fluctuate here in that free space. But I can't go from here all the way to the other side. I have to go through too many intersections. That's really how the structure comes to the natural disorganized state. Now, I brought these because you asked me the question between steel and copper and aluminum. The steel that we know at ambient temperature, we're not talking about stainless steel, we're just talking about a perlite, a normal structural steel, has this microstructure instead of the black pieces here for copper and aluminum. So you have fewer slip system in a structure like this than you have here. The high density planes and direction, you only have 8 here and you have 12 there. So the mobility, the ability to do just about anything you want is reduced with steel as opposed to aluminum and copper. And it's advantageous because you can weld steel. It doesn't have any dislocation really in the weld. It's just an as-cast structure. When you go to aluminum and copper, they just become really, really soft if they're not processed to develop strength because it's easy to deform them. They have more slip systems. And at low temperature, it becomes more significant because everything I've talked about, forming this and just the Frank Reed sources, where were they? Is it here? No, it's that schematic. I think you can appreciate all this stuff here will be influenced by how much time you allow for that to take place and what temperature you're at. The higher the temperature, the easier it is for the dislocation to keep jumping and moving around. At ambient temperature, you really need a force. But if you heat it up, it could start doing it on its own just based on the little residual stresses in that grain. The local misfit stresses will make it restore and recover. So if I had two dislocations that were moving in different directions, they're a little bit apart, and I heat it up, eventually they come together and I lost it. Now, when we reach that point here, when we're steady, either by putting a lot of strain or being at higher temperature are the two conditions to get there, it's a point where we have dynamic recovery in the single grain. So we're going to become with a more constant density of dislocations. If you want to amuse yourself with those, you're more than welcome to. All right. Are we good with dislocations? Any dislocation questions? All right, we're moving to grains. Grains do exist, and they do make our life a little harder, but if you bear with me, I'll try to get everything to make sense. Everything we talked about, the dislocation, still true because we have a polycrystal, okay? Nothing has changed. Essentially, those vein structure, all the high density, low density of dislocation that we talked about are still true within each grain. So this is a TM image. You see the very small grain there. In each grain, you have dislocation. When the dislocation reaches the grain boundary, and it's really small, it's possible sometimes for the dislocation to get in there, to get in the grain boundary. But there is a lot of energy there, and a lot of times it will just stay in its own grain. So don't think of, oh, the dislocation is going to go from one side to the other of the piece. That's never going to happen. It's confined to its own grain, and it could go to the grain boundary. It happens more when you have very, very fine microstructure. Now, having said that, I think we can all appreciate that if I make the grain smaller, there's just a lot less room for the dislocation to move with respect to the other in that grain. So grain refinement essentially confines this system of dislocation more. And on this plot here of grain size against the micro hardness, when you're decreasing the grain size, you are increasing the strength significantly. It's a known fact, and that's the reason why we like to work the metal, the steel, quite a bit before we use it, so it has a fine microstructure. It's increasing the strength, and it's also beneficial for a lot of fracture properties. So grains are important, and as you can see from this, the more grains, the better it is. So don't think too much of them as a weak point in the material. They can be a weak point if there's hydrogen in the system and all of a sudden you start cracking at the grain boundary, for example. But these are exceptions. The general rule is you want to have a lot of grains and fine grains to increase your strength and your general toughness. Now, how do I get them is really what I want to guide you through a little bit today, and this is something we're going to continue tomorrow. I'm showing here what happens with respect to your strength and ductility as function of the annealing temperature. Annealing really just means you heat it up. That's what happened to those copper pieces that have been circulating around. They were heated up to different temperature, so they went through different processes in terms of the microstructure. We're looking here essentially at something that was rolled, so all the grains are very elongated to begin with. It's the same with the sample that's in the metal and what I circulated, that's on the form. You start, there are advantages between cold rolling and hot rolling. When you cold roll and you make a certain shape, let's say I make a sheet, it looks perfectly flat, it stays flat, right? Because there's nothing else going on. If I do it the same process warm, when I cool it off, it's going to tend to have some curvature. So the dimensional tolerance on hot rolled products is not as good as on cold rolled product. Well, if we start going into all these details, we'll not be done today, but let's go back to this. We deform the microstructure and then we annealing, so we just eat it up. And we'll talk later about what happens when you heat and deform. But for now, we're just eating it up. The grains that are there, they have so many dislocations in them that the first thing that's going to happen is, of course, you're going to have some of that recovery process. So two dislocations of opposite Burger's vector, different direction, will combine to make nothing, to essentially reduce the internal energy in your structure. That's the driving force. That tends to be not all that big. It's hard, depending on the temperature you're at, it's hard for the dislocation to move. If you do it at relatively low temperature for a long period of time, that's where you can get that done. But a lot of times what we end up doing is we eat up enough that we get in this recrystallization mode. Recrystallization means a little bit like you form ice. Yeah, you kind of form ice on the windshield. You have a little one starting in one place, another one starting the other way. It's consuming the liquid. All of a sudden, you don't see anything anymore. This is what happens here. There will be one grain that's just is popping out at a corner. There was just so many dislocations. Decide, you know what? I'm going to just reorganize myself, and you're growing a new grain that has a different orientation than all the grains around it. Now, it takes time, it takes movement, but the driving force is all of a sudden when you through that process, it's a little bit like my room is full of crap and I gradually start moving into the storage unit and I organize it. So as I go, I'm really reducing the level of disorder, but I need a place to do it. I took a certain space to start organizing myself, and that's a triggering event here. You have to need to have some nucleation site that's going to allow you to start growing these grains. When you continue doing that, eventually all these grains, if you look, are actually finer than these. You can do that if you have enough of the small nucleations of new grains. Now, if I try to go too fast in my heating process, what can happen is I'll have a few of these that will start forming, and they can grow very quickly at the expense of the others. So the number of recrystallization grains is going to influence your final grain size. You want as many nucleation as possible. We always want a very fine microstructure. So that 600-degree copper sample you see with the big peeling effect is essentially a situation where there were fewer grains that manage to form because we were at low temperature. It takes time for them to form, yet when they formed, they grew, and we call it abnormal grain growth. And it's a problem mostly with pure metals. It's a big problem for pure aluminum. We had a project where our client wanted to use pure aluminum for its ductility for medical devices, and they had tremendous problems because you deform it locally. Say you have a tube for a surgery operation, you deform it locally, and in that deformation zone, all of a sudden the grains grew very much. Aluminum is so low temperature alloy. The grains grow, and then you lost your ductility, you lost your strength. So when you try to bend it back, it's not good. So the idea of controlling what happens to your material as you keep deforming it, whether it's, I'm just giving you an example in service, but also in processing. If you're in a situation where you start forming these abnormal grains that are really large, you lose the consistency and the quality of your product. So you have to be careful with that recrystallization process. The goal is great, because if I'm trying to deform from these billets that we've talked about, trying to go down all the way to something like this, if I don't have recrystallization that gets rid of my dislocation, I'm going to have to work very, very, very hard. So when I make those, normally I'm in a mode that I keep recrystallizing new grains. And that keeps the force required to make the part relatively low. I do want to emphasize, it's so amazing we can do this with metals, because I know Professor Eager, at least on Monday, was making the reference to concrete, because concrete is really, really cheap. It's an aggregate, and it's used in a very, very large volume of civil structures. But one issue with the concrete, unless you, as an undergrad or graduate student, find a way to do similar with concrete than we do with metals, you're stuck with what you cast. So over here we have some aggregate, we have multiple faces, we have grains. Concrete, the Portland cement is a very complex microstructure that has some crystalline parts. What typically happens once you dry the concrete and it cured, you have some environmental effects that are going to continue to affect each of the different phases, but nothing is really going anywhere. I can't eat this up and say, I'm going to change it completely. So it's a big advantage that we have with steel, and we should literally make as much as possible out of it. The idea that you can deform, do anything here? No. Isn't that great? I'm the only one who can see it. I think it's good to see, so let me take 1 minute here. Okay. The rolling operation, which is pretty much where we're going here in terms of being at temperature and stuff, is typically done subsequently. You know, you would think you would cast and then try to use the bullet and feed it into this process, but most of the time it's stored temporarily, and then they go on to the high temperature process. Because of the amount of deformation you generate, typically you don't have to heat up the material as it goes through these processes. You know, you're in the shop, you have a lot of radiation heat, you lose heat, but the plastic deformation, all this multiplication of dislocation generates heat as well. So the main idea is we make a lot of use of, you know, the recrystallization, the grain movement, the effect of plasticity. The main objective being you need to homogenize the microstructure, and you also want to get to the shape you want. You typically don't want a billet. You want one of these sophisticated shapes. Maybe you want that canister for propane. This piece is actually from the bottom all the way up. It's a little bit like a soda can. It's made out of steel. If you need to be able to control your strain hardening, your behavior of the material, so you don't poke hole, you don't have instability when you start making this. And we're going to talk about that tomorrow. Thank you a lot for the questions, and I hope you learned something.